Hey,
Hello there. Number 5.
enthalpy and table I. This is where I should pull out those 20 blank pieces of graph paper,
Oh my goodness.
make you graph all the heats of reactions,
Ooh, I'm
put
going
the
to,
products and the reactants on the correct side.
as your elected chemistry professional, I'm going to lobby that he doesn't do that on behalf of you.
I'm going to slay them, Milks. Graph until your finger
Oh
bleed.
boy. Reading heats of reaction. So there's a lot to write here. So take your time. If you got to pause it, by all means pause it. But you need this. Okay. The delta H of a reaction is the sum of the total energy absorbed to break the reactant's chemical bonds to form this activated complex, which is just a noun. You don't need to be able to tell me what the chemical is. And then the energy is released when forming new chemical bonds as products.
Right. And the way I look at it is this. If I got to get these particles that are connected in a bond over here to react with these ones to produce that different chemical over there, all these chemical bonds need to break.
So we got to add a little bit of heat energy to do that.
Activated complex. They'll find their new partners in their new places.
And then when they rebond, they release all that energy. And here we go. And we track that is all we're really doing.
The heat of the reaction.
Right. And here you go. We got this one right. Products minus reactants.
Because we didn't have to spell it all out.
P's
and R's.
P's and R's are good.
Heat of the products is always going to be on the right-hand side of the reactant diagram. Reactants are going to be on the left-hand side. So
and then this magnitude, the number that we get, tells us how much energy was totally involved. Yep. The sign tells us if heat was released or absorbed.
And magnitudes are going to be in kilojoules per mole. Mole is going to show up again because we look at 1 mole of substance being formed.
Right. We generally don't do joules. We do thousands of joules at a time, kilojoules.
Kilojoules. So you look at 1 mole if it's releasing energy or absorbing energy, and you can double it, triple it, quadruple it if you have more than 1 mole.
Right. Now this goes to just like we do with balancing equations and some other things before. If I double how much stuff I start with, I should double now the amount of heat that I get out as well.
I mean, heck, if I got a recipe for a batch of cookies that says you're going to make 12 cookies, but I double all the ingredients, I'm going to make 24 cookies instead.
Right. Mm-hmm. Makes sense. So if we treat heat as a product or a reactant,
makes sense.
Makes sense. And if we half the amount, then guess what?
Only make 6 cookies if I cut my ingredients in half.
Again, we've actually kind of talked about how we manipulate this in the past. This is almost a review. It's almost a review, I tell you.
Sure is.
Now here's the other piece. Now we reverse the reaction.
Right.
So if I run it backwards, what do you think is going to happen to the heat?
The same amount of heat, but it's no longer released, it's absorbed. Like if you can remember, like what's hot on Instagram right now is the videos that go forward, back, and forward. There's a little thing. That's what you do. If you're going forward and you're positive, then you're going to be moving backwards. You're going to be negative.
There you go. So
forward,
switch
negative,
the sign.
Forward, negative. You just switch the direction of the heat flow, really.
Endothermic becomes exothermic. Exothermic becomes endothermic.
Exactly.
There we go.
And so for a reaction that produces a lot of heat, if I wanted to run it in reverse, I'd have to force it to absorb a lot of heat.
Right.
Which is what he just said.
And some are a little bit easier to go than others. Right. Those exothermic reactions, you only got to add a little bit of heat to get them up there, and then they
produce a lot.
Well, I got to give it all that heat back to undo it all and make it go backwards. A lot harder to make those go in reverse.
Yeah, it's like a reverse of an explosion. A firecracker explodes and releases a ton of heat. If I had the physical ability to force all that stuff backwards, even after it had been made, I would get a firecracker back.
Right, but luckily those things are not what we call equilibrium reactions, where the forward and reverse reaction is happening at the same time.
Right.
So there's the key here.
But in table I, most of these are all one direction reactions, I do believe.
Yeah, they are, but we're going to apply that now to our equilibrium.
Right.
Mm-hmm. Okay, which means they're both happening.
Correct.
And now we have a little bit of work to do with table H.
So here's table H. Let me find
We're going to need a handy dandy reference table.
I'll find one.
You know there's a stack of them right over there. Yeah. This is what we call a chemistry classroom. We got lots of them.
I think it's pronounced chemistry.
Oh, I don't know how you got that one.
CH makes the ch sound. My son's learning how to read.
Okay.
CH makes ch. That means chemistry should be chemistry, right?
When he can pronounce Le Chatelier's principle, we're all set.
It's Le Chatelier's.
Yeah. So let's find this chemical reaction right here. N2 gas with O2 gas makes specifically NO2 gas. Notice I'm paying attention to those states very carefully. And what
Table
you got for
I.
number for me, Mr. Monica?
N2 gas plus O2 gas makes 2 NO. Nope, that's not the one. N2 gas plus 2 O2 gas makes 2 NO2 gas. Heat of reaction, positive 66.4 kilojoules. Okay? So
positive means it is
endothermic
endo.
because it has absorbed energy compared to where it started.
Beautiful. Next one.
N2 plus 3H2. So we're going to find an N2 and 3H2s. There's N2 gas, 3H2 gas makes 2 NH3 gas. Is that the one?
Ammonia. Come on, ammonia. Gotcha.
Negative 91.8
91.8
kilojoules per mole.
Negative has got to be exothermic.
Because the products have less energy than the reactants did. It must have released a bunch of energy into the environment when that happened.
Okay.
Now, 2NH3 making N2 and 3H2. I don't actually see that anywhere. I don't see anything starting with NH3, Mr. Mills. What the heck?
This one going
in reverse.
Upwards.
Exactly. So what we said before was it's the same magnitude of energy, 91.8 kilojoules, but the sign gets flipped. So that becomes endothermic in the process because you can turn ammonia back into hydrogen and nitrogen.
Yes.
It's just that you have to force it to absorb energy to do so.
Which means I got to give it a ton of it.
Right. Versus where forming it released a ton of it. How much is a ton? The exact same amount, but released and absorbed. That's what the positive and negative signs mean. That's why they're important.
And guess what? I
think
think we're
that's
done with
it.
number 5.
Mad easy
These videos have been pretty good this whole unit so far.
for shizzle.
See you guys.
See you.